Well, thanks a lot to the organizers for inviting me. It's great to be here, and thanks to all of you for making it out in spite of the snow. All right, so the family of functionals we want to talk about today and develop a variational theory for has their origins in physics, and in particular in the study of superconductors initiated by Ginzburg-Landau in the 50s. But for an audience of geometers, I think it's a little more useful to situate them in a larger family of problems associated with the study of harmonic maps. OK, so let's just quickly recall. So given some closed manifold, let's say Mn and N, that a map between them is said to be harmonic if it's critical for the Dirichlet energy, not just our usual old friend, among perturbations with values in n, right? OK, so these come up naturally in geometry. But when we're trying to study things like gradient flows or apply more theoretic methods, we run into a lot of problems from the fact, among other things, that the space of Sobolev maps from M to N doesn't have a nice manifold structure in general. OK? So therefore, when we're trying to construct gradient flows in this kind of thing, it's useful to study perturbations. OK? So in the critical dimension, we have, for instance, a perturbation by Sachs and Uhlenbeck, where we approximate from above by p-harmonic maps, where the variational problem is a little more regular, and it passes to a limit. OK, but for general domains in arbitrary dimension, there's another pretty robust method where we take advantage of an isometric embedding of n, our target, into some large dimensional Euclidean space. And we consider on our Euclidean space some potential function which has the property that it vanishes precisely for points in our target, and it's going to be positive outside. And in practice, it's useful to put a couple more technical conditions on this, but we're not going to worry about that for now. So then, on our nice Hilbert space of Sobolev maps into this large Euclidean space RL, we can study this perturbed problem, which I'll call E epsilon sub n, where we take a given map U from M to RL, and we assign the usual Dirichlet energy, plus now a potential term. And let's put over here for this positive parameter epsilon, a 1 over epsilon squared. OK? So what do we have? Well, if we have a map that's taking values in our target, then this vanishes and we just recover the Dirichlet energy, right? But for a general map taking values in RL, we're going to have this term over here penalizing us for deviating from the target. And it's going to do so more and more severely as epsilon goes to 0. So in particular, if we have mild energy growth as epsilon goes to 0, any map is going to be forced to take values in n in the limit, at least almost everywhere. And indeed, there was work by, for instance, Chen and Struve, and Fanghua Lin and Changyu Wang, and others, which tell us that this is a good method for constructing harmonic map heat flows by perturbation, and for instance, for constructing critical points of the Dirichlet energy, modulo perhaps some bubbling issues, which are impossible to avoid. OK? But the story I want to talk about today involves the fact that the space of critical points for these energies is often much richer than the space of harmonic maps to the target. OK, so in particular, a fun example of this comes when we take the target to be the 0 sphere, i.e. plus or minus 1, sitting inside of R. OK? So in this case, We have -1 here, +1 here. And our potential function is going to look like this double well. OK, so for instance, this canonical example would be w of t is 1/4 1 minus t squared squared. OK, so the function that we get in this case now takes scalar valued functions and assigns to them what's called the Allen-Kahn energy, named after physicists who studied it in the context of phase transitions. OK? All right. So harmonic maps to S0 are themselves not especially interesting, right? If you want a 2-second exercise, you can figure out what they all are. All right. But if we're looking at families of critical points to this functional, and we don't require bounded energy, then in fact we have a really rich theory. Okay? And in fact, if we look at the space of critical points for these functionals, with energy growth of order 1 over epsilon, there turns out to be a really rich connection between the variational theory for these functionals and the variational theory of the n-1 area functional for hypersurfaces in our manifold. OK, so investigations along this line go back as far as at least the 70s with work of De Giorgi and Modica and others. All right, but there's been a lot of resurgence of interest in these lately, particularly in the work of Marco Guaracco and the program he initiated. So in his thesis, I think this is around 2015, Guaracco studied a natural mountain pass construction for these functionals on a given manifold. OK, so he studied particular natural min-max theory for the Allen-Kahn functional. And building on work of Hutchinson and Tonegawa and Wickramasekara, he was able to show that, in fact, using critical points of these functionals, so you can construct in a natural way a family of non-trivial critical points for the Allen-Kahn equation, OK, whose energy concentrates on the minimal hypersurface of optimal regularity. So in particular, get something which is going to be smooth away from a set of codimension 7. OK? And then in the years since, there's been a lot further progress. So more by Guaracco, by Pedro Gaspar, Fritz Hiesmeyer. And last year, there was some great progress as well by Chodash and Mantoulidis, in which they proved that, in fact, generically, these minimal hypersurfaces will have multiplicity 1. And what's very nice about this theory is that, well, ultimately, the minimal hypersurfaces we construct have the same structure as the ones we get from the geometric measure theory min-max of Almgren and Pitts. On the variational side, the work is much simpler, right? Because now we're working with nice smooth functionals on a Hilbert space to which we can apply classical mountain pass and Morse theoretic methods very easily. And somehow all of the technical burden is instead shifted on the asymptotic analysis of critical points for these functionals. OK? So a natural question then is, can we do anything similar in higher codimension? So in higher codimension, it was shown by Almgren in the 60s that indeed we do have stationary integral variafolds of arbitrary codimension in a given manifold, all right, relying on a somewhat complicated geometric measure theory min-max construction. So the question now is, can we find some analog of the Allen-Kahn construction in this setting, which allow us to do a similar thing of shifting the technical burden of the asymptotic analysis of critical points for some nicer functional. Okay? And I think before going anywhere, it's useful to say that there is not going to be a straightforward analog of the Allen-Kahn equation in higher codimension. Okay, so things aren't going to work out as cleanly. But there is a good candidate with a rich history in codimension 2. Okay. And so this brings us to the functionals advertised in the title. The complex Ginzburg-Landau functionals. All right. So, given a complex valued map on our manifold, and again a positive parameter epsilon greater than 0, we define the complex Ginzburg-Landau functional, parameter epsilon, in a way that formally is going to look identical to our Allen-Kahn functional. So we have a Dirichlet energy, and we add now this potential term, 1 over epsilon squared times 1 minus modulus u squared squared. All right, but now, instead of this double well, recall that we're working on the complex plane. So instead, if I can draw this reasonably, we get this circular well potential, where our 0 set is going to be our nice unit circle inside of C, right? So it's perhaps worth noting, OK, so in the framework we discussed before, we can think of this as a perturbation of the harmonic map problem for maps into S1. OK, so perturbation of the variational theory for the Dirichlet energy on S1 valued maps. All right. So perhaps before doing anything else, we should recall what our actual harmonic maps to S1 look like. Okay? So certainly, the space of circle-valued maps is at least a little bit richer than the space of maps to S0. But the space of harmonic maps to S1 is still quite rigid. OK, so given an S1 valued map, u from M to S1, OK, well, the gradient is completely determined by the one form, OK, which we'll call ju, just given by pulling back the unit form on S1. OK, and we note, of course, that this is going to be closed. And it's easy to see that our map u is going to be harmonic if and only if this one form ju minimizes the L2 norm in its cohomology class, i.e., harmonic in the usual sense. It's closed, it's also co-closed. OK, so in particular, if we take any harmonic one form, so given some harmonic one form h in our manifold, if it also has integral periods, so if we know that it's integral around any loop, takes values in 2 pi z, well, then we can integrate it to get our harmonic S1 valued map. OK, so in particular, modular rotations, what we see is that our space of harmonic maps to S1 mod out by rotation is just going to be one-to-one correspondence with harmonic one forms in this lattice. Okay, which we can identify, if you like, with the integer cohomology in degree 1, which of course is just the homotopy classes of maps to S1. Okay, so in particular, life is very simple. We have a minimizer in each homotopy class, which is unique up to rotations. Okay? So in particular, the space of harmonic maps here, well, it's nice, but it's not especially rich, right? We get all our information from the cohomology. But similar to the Allen-Kahn equations, the actual space of critical points to the Ginzburg-Landau energy turns out to be much more rich than these harmonic maps alone. Okay, so to get a feel for this, let's consider a variational problem that received a lot of attention in the 90s. It was popularized in this 94 monograph of Bethwell, Breziz, and Delaine, although others also worked on this question. So consider the following. So let's take a nice self-map of the circle to itself. And let's ask that this have non-zero degree. So we want something homotopically non-trivial. So then we want to know, what do the minimizers of the Ginzburg-Landau functionals with respect to this boundary condition look like? On the disk, that is. What do these look like as epsilon goes to 0? OK? So what do we know? Well, we know that since we have non-zero degree, certainly we won't expect an honest harmonic map in the limit, right? We're going to have singularities. And those singularities are going to force some amount of energy blow up. OK? So the question then is, how badly does energy blow up? Yeah, that's right. So now we're working on just the disk. Thank you. OK, so how badly does energy blow up? And can we actually say something meaningful about the limiting behavior of the minimizers? OK. So to get some intuition, let's try a special case. So let's see what happens if we just take, for instance, our boundary map G to be the identity on S1. OK? So if we ask analogous questions for maps from the ball to the sphere in higher dimensions, then we know that our energy minimizer is going to be given by just the radial extension of the identity into the ball, right? So we might expect that our minimizers U epsilon are going to approximate this radial map taking z just to z over its modulus as epsilon goes to 0. OK? So following that intuition, let's try a simple regularization of this guy. So let's consider the maps v delta on the disk, where we can send z to z over z, just this radial extension, outside the ball of radius delta, and then just regularize in the most naive way we can think of, say take z over delta inside that ball, right? So the picture, here's our unit disk. Here's our disk of radius delta. So out here, we're just given by the radial map. And then here, we're regularized to something with gradient bounded by 1 over delta. OK? So let's then compute our Ginzburg-Landau energy. So what do we see? Well, if we compute on the annulus outside, OK, so if we compute energy of this v delta, over this annulus from radius 1 to delta. It's not hard to see that this is going to be given by the integral of 1 over 2 times the modulus of z squared. Okay? And if you need a 15-second calculus exercise, okay, you can check that this is going to be exactly pi times log 1 over delta. Okay? Now what about on the inside disk? So on the inside, well, now our Dirichlet energy is just going to give us something like constant over delta squared, right? And then our potential term is going to give us something bounded over epsilon squared. So we'll be imprecise and say this is going to look roughly like constant over epsilon squared. OK, so then taking into account the area of the disk, we have something that just looks like a constant plus a constant times delta squared over epsilon squared. All right, that's all fine. OK, so we see that our energy for this map V delta is going to be pi log 1 over delta plus a constant plus some delta squared over epsilon squared term. And it's another 10-second exercise. You see this is going to be minimized when delta is a constant multiple of epsilon. OK? So we expect our minimizer, at least in this naive family that we're looking at, is going to look like something that's simply a harmonic S1 valued map, namely this radial extension, outside a disk of radius O of epsilon, and then inside some regularization, which makes a bounded contribution to the energy, right? And in particular, we expect our minimum energy to look like pi log epsilon plus bounded terms in the limit. That should be a big O. OK? So that's our cartoon picture. And it turns out this actually isn't a bad cartoon. OK? So the analysis of Bethwell, Brézy, and Alain in their monograph tells us that indeed, in general, our minimizers U epsilon will have energy given to leading order by pi times the degree times log 1 over epsilon plus bounded terms, which one can say more about, but we won't today. OK? And moreover, away from exactly d singular points, A1 through AD in the disk, our U epsilon converge smoothly to some U star, which is going to be a harmonic map, again, away from these singularities from the disk into S1. OK? And finally, it's useful to note that these singularities are actually determined by a finite dimensional variational problem. So that in principle, we can determine exactly the optimal configuration of singularities for this generalized energy minimizing map. OK? And so for instance, in our toy case, indeed, the minimizer in the limit is just going to be the radial extension. OK? So it really is a reasonable notion of a generalization of energy minimizing extension, even though we don't actually have finite energy extensions to play with. OK? But the takeaway for today is that we can expect this log epsilon energy growth to correspond to some kind of codimension 2 pattern formation around these singularities. Right? So we can ask what the things look like when we study the variational theory for this problem in higher dimensions. Okay, so in higher dimensions, it turns out that, again, critical points of this functional, i.e. solutions of the complex Ginzburg-Landau equations, I should go ahead and write down. These are going to arise naturally from variational methods. Okay? And in particular, we naturally get solutions with energy growth of order log epsilon. And what we find in higher dimensions is that these singular sets here, which in this case were constrained to satisfy a finite dimensional variational problem, now we see that our codimension 2 singular sets in the limit are going to look like minimal submanifolds of codimension 2 in some weak sense. Okay, so our energy concentration set will happen along weak minimal submanifolds of codimension 2. So I believe the connection between the problems, at least for energy minimizers, was first observed by Riviere in dimension 3. So observed there were connections between minimization problems of the Ginzburg-Landau energies and the construction of minimizing geodesic networks in 3 dimensions. And then in higher dimension, for minimizers, there was work with Lin and Riviere, where they showed that an analogous statement is true in higher dimensions. So for instance, one can always solve the codimension 2 plateau problem in a convex domain. So you can produce solutions of the n-2 plateau problem, at least in convex domains, via energy concentration for minimizers of these Ginzburg-Landau functionals with suitable boundary conditions. Okay. So one of the key ingredients in their analysis, which is somehow the analog of an epsilon regularity type theorem in this setting, is this result, which is called the eta compactness result in their work. So the eta compactness theorem, which tells us that near the 0 set, we have to have energy blow up at least of order log epsilon. Okay, so in particular, if U epsilon solves the Ginzburg-Landau equation on the unit ball, okay, and let's say U epsilon of 0 takes values far from S1. So for simplicity, let's say it's modulus less than a half. Then we have to have energy growth at least of order log epsilon. Okay. So in particular, on the other direction, this is telling us that where we don't have quantization of energy of order log epsilon, then in fact we're going to take values close to S1, and we're going to be looking again just like a harmonic S1 valued map. Okay. This is really a key analytical ingredient. And this was later extended to critical points in arbitrary dimension by Bethuel, Brézy, and Orlandi. And in fact, by combining their analysis in the setting of compact manifolds, one finds the following. OK, so if U epsilon is a family of solutions to our Ginzburg-Landau equation, on M with energy growth of order log epsilon, then if we study the normalized energy measures, so we look at our energy density and normalize by log epsilon, then subsequently, as epsilon goes to 0, these will converge weakly as radon measures to some limiting measure mu of the following form. OK, so we have first our concentrated part on this n-2 submanifold sigma, plus we have a diffuse part given by the energy of a harmonic 1 form times the volume form. OK? Now I should make a few remarks here. So again, clarifying a little bit about the structure of this limiting measure, we have that H is just a harmonic 1 form. OK, this set sigma is n-2 rectifiable. And we can realize it as at least the Hausdorff limit of the 0 level sets of u epsilon. OK. This theta is just some positive multiplicity function on sigma. And then moreover, and this is the key point, the pair sigma theta is going to be a weak minimal n-2 submanifold. So specifically, this is going to find a stationary rectifiable n-2 varifold. OK, and all this means is that if we look at the weighted volume functional, given by sending sigma theta to the integral over sigma of this density theta with respect to the Hausdorff measure, then this is going to be a critical point with respect to perturbation by diffeomorphisms of our manifold. OK? Where is H defined? So H is just a smooth harmonic 1 form on our manifold. Right. OK, so in particular,
is there something that converges to H?
Is there something that converges to H? Yes. Yes. OK, so let's make a little more comment about where these things are coming from. OK, so what's the origin of this H? So in particular, let's make a few observations. So if we have no cohomology in degree 1, well, then automatically we aren't going to have any harmonic 1 forms, right? So clearly, our mu is just going to be the concentrated part, right? So on the other hand, in general, if we have some cohomology, then it's possible that all of our measure is concentrating, or not concentrating rather, going into this diffuse part given by the harmonic 1 form. OK, so if our first Betti number is non-zero, then it's possible to find families of solutions where u epsilon looks like a harmonic S1 valued map whose degree is blowing up like log epsilon to the 1/2. OK? So for a concrete example, if, for instance, we have M is the product of S1 with some other manifold, then we can take, let's say, epsilon k to be e to the minus k squared for some integer k. And then we can check that the maps u epsilon of k defined by just sending the S1 coordinate to 1 minus epsilon k squared to the 1/2, and then just the degree k map, then in fact these are going to solve the Ginzburg-Landau equations with the desired energy growth. All right, but the limiting energy measure is just going to be half of the volume form. OK?
Is there something preventing theta from becoming identically 0 here?
So in this case, it would be identically 0, right? I mean, in this case, we'd have. Sorry? So when this is non-trivial, i.e. when our solutions have zeros, right, then this is going to be bounded below, in fact, by the constant that we get in this theorem here, OK? This theta. Of course, it's possible, as I'm saying here, that the support vanishes entirely, right? OK.
So in the example, you had like a singularity at the origin for the harmonic one.
So in that example, there's no h in the limit.
There's no h.
So see, the problem here, in that case, we have this harmonic map outside the singularity. But outside the singularity, it has bounded energy, right? So here, what's the problem? Now we have things which just look like smooth harmonic maps, but the homotopy classes are growing. OK? So we have things that look very close to the minimizing S1 valued map in a given homotopy class, but those homotopy classes are growing in such a way that we're producing this log epsilon energy growth somewhat artificially. OK? Yeah?
And they are taking values on Z as well?
Sorry, no. This harmonic one form is just a harmonic one form. Nothing special.
If you write on a loop, you don't know if it gives you an integer number or.
No. So in particular, yeah, that's maybe a useful point to clarify. You shouldn't think of this limiting harmonic form as corresponding to an S1 valued map. So
Don't you get like an S1 value map on the complement of the variety or something?
yes, so in particular, under some mild compactness assumptions. So if we assume, for instance, that the first Betti number vanishes, or let's say that our gradients satisfy a uniform L1 bound, which is reasonably natural, okay? Then, in fact, away from this sigma, we converge to an S1 valued harmonic map, and yeah, but that doesn't contribute to this H. This H happens if we have harmonic S1 valued maps which are growing out of control. Somehow there's a smooth part which is growing out of control, okay?
So does J epsilon converge to H?
That's right. So sorry? So in this case, Ju epsilon would converge to the, well, no, let's see. So what I mean to say is that, so if we look at our Ju epsilons, as you're saying, so we look at the pullbacks of r squared d theta, which we'll talk about more later, and we look at their Hodge decomposition, OK? We're getting a little bit ahead of ourselves here. But we're going to find a coexact part and a harmonic part. OK? And that H is going to be the limit when it occurs of the harmonic part over log epsilon to the 1/2. So I think that answers your question from earlier. Since H is showing up when the harmonic part of our Hodge decomposition is growing like log epsilon to the 1/2. OK?
So in your example over there, H is not trivial.
Yeah, right. So we have, let's see, so maybe this is a little hard to see from over there. But yeah, right. So our map here just looks like a constant multiple of the map sending z on the unit circle to z to the k. OK, so in particular, our h epsilon here will be like k times 1 minus epsilon k squared to the 1/2 times, d theta, basically. OK? And it's this k growth that's giving us trouble. All right. Does that make sense? OK.
Do we know more in the minimizing case or in the linear where
Yes.
theta an integer? Or?
Exactly, yeah. So that's the next point I wanted to bring up, if we're relatively happy for now with where this harmonic form is coming from, is that in the two-dimensional setting, So in 2D, there are results of Miriam Comte and Petru Mironescu, which tell us that this theta is always going to be taking values in pi times the integers. Okay? And in 3D, or excuse me, in general dimension for minimizers, then indeed we know that this theta is going to be taking values in pi n again. And it's very natural to conjecture. Okay, so it's natural to guess that this should be true in general. Okay, but this turns out to be a very subtle open problem. And in particular, I mean, there's a relationship with problems like energy identities for harmonic maps and Yang-Mills connections, but the actual analysis ends up being substantially different. Okay? And if we have time, I'm going to talk about that a little more at the end of the talk.
So in particular, in the minimizing case, we know full regularity for the minimize. For the
Yeah. Well, in particular, you have a minimizing n-2 current. So yeah.
Right.
Yeah. OK. Any questions about that so far? All right. So the point is, we do have this nice family of PDEs, which are very beloved in the PDEs and math physics literature, which produce for us some kind of weak minimal submanifold of codimension 2. OK, so it's natural to ask if we can establish a nice variational theory for them and try to flesh out a little more at the variational level the connection between the space of solutions of this PDE and the space of minimal submanifolds of codimension 2. OK? And this is the content of the results I want to present today. So first, you can observe that we can in fact use a natural two-parameter min-max construction based on the saddle point methods Rabinowitz. To produce at least some family of non-trivial critical points. And then we can show that their energies do at least grow of order log epsilon. So we have some non-trivial families to play with in this theorem I presented. Or in that proposition, rather. So this was shown independently by Darong Chung and by myself, that using this min-max construction on any compact manifold, let's say closed, there exists a family of non-trivial solutions such that their energy grows at the correct rate. So in particular, they blow up no more and no less than log epsilon. As epsilon goes to 0. OK, so at least we have non-trivial families to play with. All right, so we go over here to our theorem, or over here, I suppose. And so we note that, OK, well, automatically, as long as our cohomology in degree 1 vanishes, then we're going to concentrate entirely on the weak minimal n-2 submanifold, right? But we can ask whether we expect that to be the case if our first Betti number is non-vanishing. All right, so we said it's possible that our critical points have this obnoxious behavior, right? That they're going to look like S1 valued harmonic maps, and their degree is going to blow up like log epsilon to the 1/2, and leave us with no nice weak minimal submanifold in the end. OK, but it turns out that for solutions coming from a natural min-max construction, I'll clarify what I mean by that later, but it includes the two-parameter min-max we're going to discuss, that in fact, no matter what min-max sequence we take, we're always going to find some non-trivial concentrated part of our energy on this weak minimal submanifold. OK, so we have the second result. And it comes from an estimate which I think is of some independent interest, which tells us that for U epsilon arising from, I'll be vague for now and say natural min-max methods, then we always know that this mu includes, let's just say, the sigma in the theorem there is non-empty. OK, so another way of putting this is equivalent to saying that our min-max solutions must always have some zero set. OK? So let's go ahead and set up the construction. All right, so given M, we define a collection gamma of M of families of complex valued maps parameterized by the closed unit disk. So we send a parameter in the unit disk into a map, let's say h sub y, from M to C in W1, 2. All right, and we require that for each of these families, that if y is on the boundary circle, then our h sub y is just going to be that constant map to S1. OK, so in particular, our families are taking the boundary of our parameterization in a topologically non-trivial way into the minimizers of our functional. OK? And it's not hard to check that E epsilon, these functionals satisfy a Palais-Smale condition. OK? So now to produce non-trivial critical points, the question is just whether the following min-max constant, so we take the infimum over all families of the max energy along those families. As long as this is non-zero, then we have at least some non-trivial critical point from a natural construction. Right? This is the so-called saddle point construction of Rabinowitz. Okay, it's just a two-parameter variant of a mountain pass construction. All right, so just showing that the constants, the min-max energies, are positive is not such a tricky thing. So in particular, what can we say? Well, we can observe that for any family in this collection, if we look at the map given by sending the parameter to the average of this h sub y, well, then clearly we're going to get a map from the disk into the complex plane with the property that it's given by the identity on the boundary. And degree theory tells us then that there needs to be some y in the disk such that we have zero vector mean. OK? And then it's a straightforward application of the Poincare inequality to see that the energy of the Ginzburg-Landau energy of such maps with zero mean has some positive lower bound. OK, so what's the idea? All right, if we have zero mean, then if we lie far from 0 in L2, Poincare tells us that our Dirichlet energy is going to blow up. But if we lie L2, then this part's going to blow up. OK, very straightforward. OK, so at least we know right off the bat that these natural min-max energies are positive. Okay, and so in particular, we have some non-trivial solutions, U epsilon floating around. Okay. But to establish this first theorem, we now want to know that they actually grow at the rate that we associate with the formation of weak minimal submanifolds, right? So how can we accomplish this? Well, for the upper bounds, it's pretty straightforward once you know what you're looking for. OK, so we want to construct just some candidate families, H epsilon and gamma of m, right, such that their energy satisfies the correct bounds throughout the family, right? So the max of these energies satisfies some log epsilon bound. OK, so how can we do this? Well, first we can construct a family in gamma of the unit disk, or let's say any planar domain, as follows. OK, so we'll take a complex parameter, A and C, and just send it to the map. Well, thinking back to our picture of minimizers in the disk earlier, we send it to the map given by z plus a, or modulus c plus a, where this radius is at least epsilon, and z plus a over epsilon, where it's less. OK, so we know from our computations before that these are going to have energy bounded above like log epsilon. And if we identify our unit disk with the obvious compactification of C, it's not hard to see this gives us a family in gamma of this domain. OK? And then just pick some suitable generic map from our given manifold of choice into C. OK, and then pick some domain containing its image and compose. So we take H epsilon to be, what do we call this guy? Let's call it H omega epsilon to be H omega epsilon composed with F. OK?
I'm sorry.
Yeah.
What do you mean by d squared equal to c?
So what I'm saying is I'm identifying the unit disk with a compactification of C in sort of the obvious way, right? If we shoot off in a radial direction, then we end up at a point on S1. OK? So we're saying, for instance, that Zj is going to, let's say, theta in S1 if Zj over Zj is going to theta. OK? So I'm just saying map the closed unit disk, map C into the closed unit disk such that this is true. OK? So we're just squashing it radially.
It's certainly not normal. It's smooth.
Sure, well, continuous is all we need, right? We just want continuous families. OK. Is that good? OK. All right. So the lower bounds require a little more thought. So first of all, if we could show that any non-trivial family of critical points has log epsilon energy blow up, well, then clearly we'd be done, right? We'd be happy. But we know, again, from our examples where we have some non-trivial cohomology in degree 1, that we can, in fact, have U epsilon non-trivial critical points of bounded energy as epsilon goes to 0, which are just converging to some harmonic S1 valued map. OK? But
So you want to show that this does not happen?
I want to show that this isn't going to be the case for our, yeah. OK. All right. But the point is, if we just have a family of non-trivial critical points, a priori they could do this, right? OK. Fortunately, it turns out if the first byte number does vanish, then any non-trivial critical point has a 0. OK? So once we establish that claim, it'll immediately follow that at least in the case where the first byte number vanishes, we have some log epsilon energy blow up. OK, so how do we check this? OK, so again, let's observe that if u epsilon has no zeros, then we can consider the map to S1 given by just taking u over its modulus. And now let's observe is that it's not hard to compute that for solution of the Ginzburg-Landau equation, the one form ju epsilon is going to be coexact. OK? So in particular, we know that if we pair with any exact form, we vanish. And I'll just mention this is equivalent to the fact that u is critical for e epsilon under perturbations of the form e to the I phi u. OK? All right. So that's an identity we have floating around for our solutions. But now, if we look at the pullback jv epsilon for this associated S1 valued map, well, this is going to be closed. This is just the pullback of a closed one form on S1. And then since we're working in the case where we have no cohomology in degree 1, it has to be exact. Right? OK, but we can also check that jv is just u to the minus 2 times ju. OK, so if we plug in jv epsilon here, then we find that this positive integrand is going to vanish. OK, so in particular, our S1 valued map is constant. And then it's not too hard to play around with the maximum principle and see that, in fact, the full map u epsilon then has to be constant map to the circle. OK? So any non-trivial critical point has to have zeros when our first byte number vanishes. But then this tells us that on the sphere Sn, we have at least a desired energy growth. This is blowing up like log epsilon. OK, and then there's a little two-step argument to say that, in fact, we have desired energy growth for the min-max energy on any manifold. OK? So first, we can consider the upper hemisphere, say. And then we see that for any family in gamma of the upper hemisphere, we can associate a family H twiddle on the sphere simply by reflection. OK, and that's only going to double the energy. OK, so in particular, we have that C epsilon of Sn plus is going to be at least half C epsilon of Sn. And now we're fine, because given any m, we can just pick our favorite ball inside M, identify it in the bi-Lipschitz way with the upper hemisphere. And then for any family on M, we spit out a family on the sphere for which we have desired energy bound. And so we get finally desired lower bound on these energies in the limit. OK?
So when you say Sn plus, there's no boundary condition.
No. This is, so you think of this as free boundary, right?
It's sort of like a
Yeah. OK. All right, so we know that we have a family of solutions to play with. They occur naturally, so we're not just generating these at random. And we know that under some topological constraints, these are giving us weak minimal submanifolds. OK, so in the next half, we're going to want to show and introduce some fun new estimates along the way that in fact we're always going to get some non-trivial weak minimal submanifold in the limit. Okay, and in order to do that, we're going to have to estimate the amount of Ginzburg-Landau energy it requires to transfer between different homotopy classes of S1 valued maps. Okay, I think that's a good time for intermission. So recall now that we have this family of solutions. We want to rule out the following pathological behavior. So we want to rule out the case where U epsilon looks like a harmonic S1 valued map, which is jumping around in homotopy class. Okay, so whose degree is growing like log epsilon to the half. Okay. And we said that we can't rule this out for general critical points, right? So we're really going to have to employ, in a non-trivial way, the structure of our min-max construction. So what do we note? We note that any family, by definition in our space gamma of M, has to pass through the constant maps, right? The constant maps to S1. So the question then becomes the following. Given a path of maps, complex valued maps from our manifold, such that V0 is some constant map, taking values in the circle, and V1 is a harmonic and non-trivial, and in particular, therefore, homotopically non-trivial S1 valued map. All right, then we want to show that in order to pass between them, before we reach this harmonic endpoint, we have to pass through something with still larger energy. Okay? So we have to exceed the energy of V1 by some positive multiple of log epsilon. Okay? So then morally, this is telling us that we can't expect our min-max solutions to look like these harmonic S1 valued maps, because if we're looking at our family, well then if we have, if we approach our min-max guy, if it's given by this harmonic S1 valued map, then before we reach it, we have to pass through something with still larger energy. Okay? So that's the rough idea. So how can we accomplish this in practice? So I think I've written it up a few times now, but recall that for a complex valued map, in fact, for now, let's restrict to maps taking values in the disk, and certainly we can always do this for our games. We define this one form JU. Notation may seem strange, but it comes from the physics side of things. Okay, to be the pullback of r squared d theta, okay, which we can write also just as u1 du2 minus u2 du1 if you like. Okay. And then let's look at the Hodge decomposition. So in general, we have that Ju is going to be given by harmonic term plus an exact term plus a coexact term, right? And we recall that if u is S1 valued, well then we know that d of Ju is 0. This is just a closed form. And moreover, we know that we have to have integral periods. So for any loop in our manifold, we know that the integral of Ju, which is going to be the same as the integral over gamma of h of u, has to take values in 2 pi times the integers, because in particular it's just going to be given by the degree of this composition. Okay? So let's define this lattice lambda sitting inside the space of harmonic 1 forms to be all of those h and h1 such that this is true, right? We have integral periods. So we know that for every S1 valued map, our harmonic form h of u is going to take values in this lattice. Okay, so in particular, it's clear that if h of u is going to be far from this lattice, well then necessarily our map is going to be somehow far from an S1 valued map, right? So the goal is to somehow relate the distance of h of u from the lattice to the blow up in the Ginzburg-Landau energy. Okay, and that's going to be done in the following proposition. All right, so if u is a map to the disk, let's put some mild energy bound on it. So we'll say the Ginzburg-Landau energy is bounded like epsilon to the minus a half. Certainly in the energy regime we're in, that's going to be fine. Then we have that the Ginzburg-Landau energy of u is bounded below by half the contribution coming from the harmonic form h of u plus some geometric constant times log epsilon times the distance between h of u and the lattice in whatever norm you choose. Okay, and then minus some term here that's not going to be interesting, so some positive power of epsilon. Okay? And so once we have this in place, what's the idea? So to complete the proof of theorem B, we want to know that if we have Vt again connecting V naught constant to V1 harmonic and homotopically non-trivial. Well, then we know that h of V naught, which is of course just 0, and h of V1 have to lie at different points in our lattice, right? Because they're homotopically distinct. All right, so in particular, as we connect them, we have to pass at some point through a point in the dual lattice, which is going to be a bounded distance from h of V1. Okay, so we have some V sub t here, such that h of Vt is going to be a bounded distance from h of V1 in L2. And moreover, such that the distance of h of Vt from our lattice is going to have a positive lower bound. Okay. And since we know that the maps coming from our min-max constructions are going to have a uniform log epsilon energy bound, when we then play around with estimating the energy of Vt and comparing with the energy of this h of V1, which is just going to be given by the L2 norm of h of V1 squared, okay, then we get this, this schematic that we wanted, that we have to pass through something which exceeds the energy of this harmonic guy by a log epsilon amount. Okay? All right, so the main goal now is then to establish this proposition. So where is this coming from? So for simplicity, let's just take our manifold M to be the n torus. Makes life a little bit easier, but the ideas are all the same. All right, so then we know that our lambdas lambda well, excuse me, our lattice lambda is generated by our one forms alpha 1 through alpha n, just given by pulling back the unit one forms from the S1 factors. And so in particular, we can choose to use, let's say, the Boxcar norm on our space of harmonic one forms, so that the distance from h to lambda, if we write h in coordinates as ai alpha I, is just going to be the max distance from these ai's to z. Okay? So now, suppose we have some arbitrary map from M to the disk, where M is the torus now. Okay. And let's say, without loss of generality, that the distance from h of u to lambda is just given by the first coordinate. Okay? So we just have the distance from, let's make this sensible, the distance from ai to z. All right. Then what do we see? Well, if U has small Ginzburg-Landau energy, in particular if it's not growing any worse than epsilon to the minus a half, then we can show that, so let's define for each y in the m-1 torus, let's define a curve gamma y to just be the first coordinate curve in our Tn. Gamma y of t is just ty. Okay, so then we can check the straightforward computation that the maximum of our potential W on the composition of U with gamma y, so the maximum of this potential on our curve, is going to be bounded by a constant times epsilon times the energy of U on this curve. Okay? All right. But then in particular, it follows that on most of these curves, our map is going to be lying uniformly close to S1. So for instance, for epsilon sufficiently small, it follows that we have a set G of U of y inside our n-1 torus of measure at least a half, the measure of n-1, such that U is at least within a half of S1 everywhere on the curve. Okay. Well, now, once we know that that's the case, let's look at what happens. So if we have some such y, and we look at the integral of ju over gamma y, okay, well, the integral over a loop doesn't care about our exact part. So this is just going to be the integral over gamma y of our harmonic portion plus the coexact term. Okay. But then we know that our harmonic integral over gamma y is just going to be our coordinate a1, right? Or better yet, 2 pi a1. So this is just 2 pi a1 plus now the integral of our coexact portion. Okay? So the idea then is that, excuse me, let's then also note that this is going to be, let's see, if we rewrite this as u to the minus 2 times the pullback of d theta by u over u, which we can do because we're bounded away from 1/2 here. And we note that this is just j of u over u plus 1 minus u squared, or u squared ju of u. All right, putting these things together, what do we note? We note that here we're integrating the pullback of d theta for an S1 valued map over the curve. So here we get something which is just 2 pi times the degree of u over gamma y plus this extra term over here, but it's easy to see that we can control this by epsilon times the Ginzburg-Landau energy over the curve. Okay? So what does this tell us? This tells us that our integral of our ju over any curve, at least in this collection of gu of curves, is going to be very close to 2 pi z, but if our harmonic term is far from the lattice, then our coexact term has to compensate. So in particular, if we put all this together, and we integrate over the y in the set g of u, let me make sure I get my estimate right. We get the following. We get that the L1 norm of the coexact part is going to be bounded below by 2 pi times the distance of h of u to the lattice, and then minus possibly some epsilon times our total energy. But recall we're assuming that our epsilon is bounded above by epsilon to the minus 1/2. Excuse me, that our energy is. So we get minus c epsilon to the 1/2 here, something small. Okay? All right, so we wanted some extra log epsilon blow up in our energy. We have an L1 bound on the coexact part of this Hodge decomposition. That's maybe not entirely clear at first why that's going to do it for us. So let's observe the following. So there's some key estimates in the Ginzburg-Landau equations due to Girard and Sohner, which tell us that if we look at the Jacobian 2 form given by the d of ju, okay, this is just 2 du1 which du2, then, okay, well first to see we have a pointwise bound by the Dirichlet energy density, right? And so it's easy to see that we have an L1 bound by the unnormalized Ginzburg-Landau energy. But the key observation of Girard and Sohner is that if we push down, instead of looking at a C0 star bound, we push down to a C alpha dual, then in fact we can estimate d of ju in the dual of C alpha for alpha and 0, 1 by some constant times now the normalized Ginzburg-Landau energy. So we get our log epsilon coming out, and then possibly with some little epsilon to a positive power here. Okay. Well, so then in particular, this is going to tell us that if we choose some qn between n and infinity, well then by Sobolev embedding, this tells us that if we look at the dual W1 qn norm of d of ju, well this is going to be controlled by the C alpha norm for some alpha, right? The C alpha dual norm that is. And so in particular we get some constant times, again, the same right-hand side. Okay. And so what's the punchline here? Well then, if we let Pn be the Holder conjugate to Qn in 1 n over m minus 1, then LP regularity for the Hodge Laplacian and a little duality argument show us that we can bound the coexact term in LPn by some constant times this W1 Qn dual norm of d of ju, right? So in particular, we get a constant times this right-hand side here. Okay. So now we're starting to see where the kind of estimates we want are coming from, right? Because we're on a nice closed manifold, so we know that our L1 norm of d star psi is going to be bounded above by this LPn norm. And now we're starting to see some energies over log epsilon coming out. Okay? But there's one more problem. If we just wanted to ignore this harmonic part and just get this log epsilon blow up in terms of the distance, then this would be enough for us. Okay? But the problem is we want to incorporate the energy contribution from the harmonic part into our estimate. So it won't suffice to apply these estimates to U exactly, but to an auxiliary map which somehow strips away the large harmonic part. So what do I mean by this? So given this U, we know there's going to be some lambda in the lattice, which is going to be our nearest point in the lattice to h of u. So in particular, such that the distance from h of u to lambda is exactly the distance from h of u to the lattice. All right, but if lambda is in the lattice, then there's going to be a harmonic S1 valued map such that the pullback of d theta by this map is exactly lambda. So what we do then is we strip this phi off of our map U. So we define this auxiliary map U tilde to be phi inverse in the complex multiplication sense times U. Okay? And then what's the trick here? So if we compute Ju, or J tilde U rather, we see that this is going to be just Ju minus U squared J phi. Okay. So in particular, since U is going to be close to 1 most places, we're for the most part just augmenting Ju by what looks like a harmonic 1 form. Okay? So in particular, since we know that h of u is going to be exactly J phi, just this lambda, plus some h prime, which is going to be bounded in L2 or any norm we like, right? Plus some bounded term such that its norm is exactly this distance, right? Okay, so we can rewrite this. Well, if we get the Hodge decomposition of Ju, then we get d star psi plus d phi. And then here we have h of u, let's say minus lambda. So we're stripping away the large contribution here, plus 1 minus u squared lambda, right? This 1 minus u squared is going to be something we're going to be able to control. So this is going to then tell us a few things. It's going to tell us that the coexact part of Ju tilde, so let's say d star psi tilde, minus the coexact part of psi is going to be small in L2. And let me make sure I get this right. Right, yeah, so we see that these are going to be bounded by some epsilon times our energy. And why is this nice? So this then tells us that if we look at their exterior derivative, so d of Ju tilde minus d of Ju in the dual norm of W12, then these are going to have the same control. So in particular, these estimates that we had for this term d of Ju in this dual Sobolev norm are going to carry over with some mild errors to our d of Ju tilde. And now in particular, we get this for the contribution of energy just from our U tilde, where we've stripped away the large harmonic contribution. Okay. So then finally, it's just a matter of comparing the energy contribution from our U tilde to the energy contribution from our map U. Okay, and then since they're only going to differ by these Ju terms, and we know that all we're doing is strip away this J phi part, what we find is that E epsilon of U is going to be bounded below by half the L2 norm of HU plus the energy of U tilde, and then minus possibly some lower order terms. So let's say dist from H of U to lambda. So we're going to get the difference between the harmonic parts, and then minus some epsilon to the gamma. Okay? So then finally, we combine this estimate with U replaced by U tilde. With this estimate here, for which we had a lower bound by the distance from H of U to lambda, and we arrive at the estimate we wanted in the proposition. Okay. So it may be interesting to remark that we're doing this in service of studying this two-parameter min-max. But of course, these two homotopy classes give us another natural min-max to study, right? So we can also study families of precisely the type we're describing. So for any non-trivial homotopy class, we can study families of paths of maps connecting some constant map to a non-trivial homotopy class. And I'll remark that it's natural to expect these kind of things to occur by the analogy with the Almgren min-max. Because if we look at loops in the space of integral n minus 2 cycles, right, in our oriented manifold, Well, Ombrand's dissertation tells us that this is going to be isomorphic to the n-1 homology. Right? But of course, this is just by Poincare duality. The same as the integer cohomology in degree 1. Okay? So it's natural to expect our non-trivial homotopy classes of S1 valued maps to be producing for us these non-trivial one-parameter min-max solutions for the Ginzburg-Landau equations. Okay? And in fact, it is possible that if we define, so given, let's say, a homotopy class from M to S1, it's possible to show that if we define the CF to be the infimum over all such paths, the max energy along that path, maps connecting the constants to this homotopy class, then in the limit, we normalize by log epsilon. These are in fact going to be bounded below by pi times an appropriate variant of the min-max mass over this space. So I'll just say if we denote by psi of h the corresponding class in here, or some discretization thereof, and we can bound this below by pi times the min-max mass associated to this class of discrete loops. Okay? So finally, as promised, I want to talk a little bit more about this problem of integer densities. Okay, and to do that, I think it would be useful to review some main ideas of how the proof works in dimension 2. Okay. So for the solutions of the Ginzburg-Landau themselves, sure, you get index bounds, right, because it's classical. For the limiting guys, so there are results of Nam-Le, which tell you that if you have Ginzburg-Landau solutions converging to a smooth minimal n-2 submanifold, then you get some index bounds in the limit. If we don't have smoothness, which is of course, it's difficult to say that we do, then it's not clear. Okay? Any other questions on this before I move on? All right. So in dimension 2, the integrality question boils down to the following. So given, say, some solutions u epsilon of the Ginzburg-Landau equations, say on the unit disk, such that their energy is, of course, bounded by log epsilon, and the limiting measure is converging to some constant times a Dirac mass at the origin. Then we want to know whether theta takes values in pi times the integers. Right? Okay. So right off the bat, something you can show by the work of Bethuel, Brézialin, and many others who worked on this, is that given the appropriate energy bounds, we can say that the space of zeros, the set of zeros, let's say more generally the set where our modulus is less than a half, is contained in the union of some bounded number of disjoint disks of radius O of epsilon. Okay, so we have some bounded number of disks, and our zero set's contained in these. So then with some effort, you can show that this density theta, if we divide by pi, is going to be given in the limit, well, first by the sum over these 0 sets, so sum I equals 1 to n. And let's also say that kappa j will be the integer, which will be the degree of u epsilon about the boundary of this disk. Okay, so if we have these kappa j epsilons, then we can say that our limiting density is going to be given by kappa j squared, the sum, that part's good, plus the sum over all distinct pairs of these disks of the product kappa I kappa j times the log of the distance between our distinct zeros divided by log epsilon. Okay? All right. So this part's certainly good. That's going to give us an integer. The problem is that we'd like to get rid of this right-hand side. Or that is, at least show something like our zeros are coming together at a speed either at least as fast as epsilon or slower than any fractional power of epsilon, right? In practice, we don't actually get to control the locations of our zeros exactly. So there's an argument which I believe is due originally to Brézy, Merle, and Rivière, which shows us that if u epsilon is a family of solutions such that away from 0 in the disk, u epsilon is converging to some multiple of a radial map, so some z over z to the kappa, okay? Then we can say that the potential measure pop a 2 out there, is going to converge to pi times this degree kappa squared. So note there's no log epsilon normalization here, right? This is somehow a completely different regime for the energy. But in particular, if we have log epsilon energy bounds overall, this will be bounded. And we have this quantization assuming this convergence away from the singularities, okay? And that relies very heavily on the Pohojayev identity we have for the Ginzburg-Landau equations in 2D. Okay? So what's the game? The game is then to observe. Well, let's simplify things a little bit. And let's say we're in a situation where we have 3 disks. And let's suppose that all of our centers, aj epsilon, are coming together at the same scale. So the problem is if they're coming together like fractional powers of epsilon. So let's say ai epsilon and aj epsilon are distanced like epsilon to the alpha apart as epsilon goes to 0. Okay? Well, then I claim, and it's not too hard to show, that we can find families of radii, let's say r1 epsilon growing much slower, faster than epsilon to the alpha, or excuse me, decreasing much faster, and r2 epsilon decreasing much more slowly, such that on the disks, r1 epsilon around these centers, after rescaling, then in fact we have that the u epsilons are converging to a multiple of z over z, I guess with the appropriate center. That's all right. To whatever the degree was. So we said kappa I. Okay. And moreover, on this exterior disk, which is going to contain all of our smaller ones, so on dr2 epsilon of 0, say, we have that u epsilon is going to converge to a multiple of now z over z. But now we're going to get the total degree, which is going to be the sum of the smaller ones, right? So we have kappa 1 plus kappa 2 plus kappa 3. OK? And so now what do we observe? So this tells us then that if we look at the sum from 1 to 3 over these interior disks of our potential measure, well, this is just going to be the sum of pi times those kappa i's squared, right? OK, on the other hand, we know that on our exterior disk, this is just going to be, well, parentheses now, the sum over our degrees squared, right? OK. And then the final point is that this potential measure is only concentrating at an O of epsilon radius around these original disks. So in particular, on the region between this exterior disk and these interior disks, it's not going to make any contribution. I'll just say interior disks. The integral of this potential measure is going to 0. OK? So now we have some arithmetic. This is telling us then that in the limit, these have to be equal. And this tells us exactly that if we look at the sum over the distinct pairs of kappa I, kappa j, that's going to vanish. And what did we want to get rid of over here? We wanted to get rid of these sums over kappa I, kappa j for things coming together at the same bad scale. OK, and so obviously in general, we can have it be the case that these disks are coming together at multiple different scales. But if we treat each scale one at a time like this, we get the same result coming out. And if we look at every possible scale at which they can come together here, this right-hand side is going to vanish. And so all we have is this nice integer part. OK, so this was the argument of Compton-Mironescu modulo a lot of details. OK. I'll remark that paper is actually a little tough to find, but it's called Remarks on Non-Minimizing Solutions of, they said, Ginzburg-Landau type equations. OK. So what can we say in higher dimension? So in higher dimension, we're in the following situation. The conclusion in 2D is that our limiting density is going to be given by pi times just this term. All of these are going to drop out, the contribution at the bad scales. OK, so in particular, we have pi times an integer. OK, we have the integer density.
You took that for the minimax.
For any solutions in 2D with the appropriate energy balance. OK. OK. So in higher dimensions, what can we do? So as Neshan alluded to, Lin and Riviere do have integrality results when we have minimization. Now, these rely very heavily on construction of competitors along a blow-up sequence. OK, so these don't transfer naturally to general solutions. But we're in the following situation. So suppose we have, let's say, solutions u epsilon on the unit n ball. And we know now that, say, the normalized energy measures are converging weakly to some constant multiple of an n-2 plane. Okay, so it's enough to show that in this case, again, we want theta to take values in pi times the integers. So with a fair bit of work and some fun analysis, it is possible to show that for an appropriate sequence of y epsilon lying in, let's call this plane here, this n-2 plane L. So for an appropriate sequence of y epsilon in L, if we look at the perpendicular plane, Ly epsilon perp passing through y epsilon, then in Ly epsilon perp, just this two-plane perpendicular, the zero set looks like the two-dimensional case. Okay, so we can say that it's contained in some finite collection of disks. As above, and in fact, you can say the same characterization of the density. So if we have this collection of disks now in this perpendicular plane, then we have the same description. Okay, so we have some preliminary energy identity here where we can in fact say at least that we can describe our density precisely in terms of the degrees and locations of our singularities. Okay? The trouble is that in 2D we had this argument that relied really heavily on the Pohjanov identity that does not go well at all in higher dimension. Okay? So I'll maybe just leave with the following thought. So in higher D, if we assume that in fact the component of the L2 norm of our map lying along this plane of concentration, if we assume that this is vanishing in L2 as epsilon goes, then in fact something like the Compactness Theorem argument goes through. Okay, we can recover something like the Pohjanov identity. A priori, for this kind of concentration, a priori, we only know that this term is little o of log epsilon. Okay? So I got pretty excited a while back when I realized I could at least reduce to the case. So it's enough to solve the integrality question in the case where this is uniformly bounded. So squeezing everything you can out of the monotonicity, you can reduce it to the case where this is big O of 1. But for now, if you're trying to generalize the Compactness approach to higher dimensions, then for now we're stuck in this purgatory between big O and little o of 1 in this gradient term. All right. I think I'll stop there.